I just said take on faith. But again, we said that the derivative of a constant function is 0. Folks, let's listen to that real quick. The derivative of a constant function is 0. Let's listen to that. How the derivative measures how something is changing, right? The derivative measures the rate at which something is changing. Okay? How is a constant function changing? I mean, I'm not asking you to do any math here. Let's look at the vocabulary words, the English words. How is a constant function changing? It doesn't. It's constant. Constant means it doesn't change. And so its derivative, it makes sense then that the derivative of a constant function is 0. Okay? I'm going to skip through all of the basic introductory power functions because then we got down to our power rule. Okay? I did not prove this one for you. The proof is in the book. Okay? At some point I might make a video for this proof, but we just don't have time. So if I give you the function f of x is equal to x to the n, how do I take its derivative?
So that's it's
Bring
n
the
times
exponent
x
down.
to the n minus 1.
Okay. And I think I said once before, in 20 years, this is what you'll remember about calculus. It's a lot more complicated than that, but yeah. Bring down the exponent, subtract 1 from the exponent. Okay. So we did a few of these power functions. Then we talked about the constant multiple rule. Okay. The constants factor out of the derivative limit. Let's just look at that one. I didn't prove this one last time. Let's do the quick proof of it. So if I have the function, let's see here. If I write the function, let's say g of x is equal to c times f of x, okay, then g prime of x would equal the limit as h approaches 0 of g of x plus h minus g of x all over h. So think of g of x as a function that it looks like maybe like 3 times x squared, or 7 times the sine of x, or 6 times e to the x. Okay? It is a constant times a function, okay, that we're currently working with. So this would give us c times f of x plus h minus c times f of x all over h. Folks, this is an important skill that we're going to start using more and more. So notice that both terms in the numerator have a constant factor of c. What is my limiting variable? H. C does not depend on h because c is a constant. What did we say about constants in regards to limits? Constants factor out of limits. So I can write this as c times the limit as h approaches 0 of f of x plus h minus f of x all over h, which gives us c times. All right, folks, I don't have you do a lot of proofs in this class, but I do need you to get comfortable with this more complicated calculus notation. This next step I consider a completely fair game step. And if you look at the practice exam in the review, I ask you questions like this all the time. I expect you to be able to recognize this thing right here. What is that thing right there? What's that, Angel? It is the limit definition of the derivative. So what can I replace it with? Bingo! I can replace it with f prime of x. Okay. What did we just show? We just showed that the derivative of a constant times a function is just the constant times the derivative of the function. Okay. And I wanted to go through this proof. I mean, the whole proof just relies on the fact that constants factor out of limits, and the derivative is just a special type of limit. Okay. But I wanted to go through this proof because it's this step right here that I think is a completely fair game step. And sometimes it's challenging for you. So I wanted to point it out to you. Okay? Okay? If I see the limit definition of the derivative, I can replace it with the derivative, and vice versa. Okay? All right. We were flying when we were talking about this last time, so let's just take a moment to pause. Okay?
I have a question.
Yeah.
So you said we recognize the definition of a derivative and we just write f prime of x. Is that what you would actually write? Like if the constant was like 4, we would do like 4 and then f prime of x and that's it? Or
Well, and then you can continue from that. So let's jump down here. We started this problem last time. We worked through this problem last time. But let me just show you how we would take the derivative of this first term. Okay? This first term can be thought of as, and there's lots of viewpoints to doing this derivative, and that's true in this topic of derivatives. There's lots of viewpoints. I'm going to view this as the constant negative 3. The constant negative 3 times the function x to the 8th. So when I go to take the derivative of this term, what does the constant do? It just comes along for the ride. Now take the derivative of x to the 8th. Using our power rule, we found that the derivative of x to the 8th was 8 times x to the 7th. Okay? So then I can simplify that through multiplication.
we have to show that work.
Nope.
Okay.
Nope, you do not have to show that work. So when I did it in class, at the end of class last time, I just said, hey, that's negative 24 x to the 7th, and I did it in one step. So for those of you who have done a little calculus before, you've probably done this operation many, many times, and you don't even think about it. Okay? But what we're saying here is that this is if we choose to look at this term right here through the lens of a constant times x to the 8th, I just bring the constant along and then just take the derivative of x to the 8th. Yeah, great question. Other questions on that? Okay. All right, so I do want to pause a moment because this is a very important idea here. Okay. I'm not going to prove it to you. We just don't have time. It's actually a very easy proof. It's a straightforward proof, but we're running out of time. If I take the derivative of the sum of two functions, I can break that up term-wise and take the derivative of the first function plus the derivative of the second function. Okay? So you would remember this as, okay, and put it on a note card or get it tattooed or whatever. The derivative of a sum is the sum of the derivatives. Okay? Now, I have made a huge deal about these little phrases, and most of them have been exactly what you would expect. Right? The limit of the products was the product of the limits. The limit of the quotient was the quotient of the limits, provided the denominator wasn't 0. Here I've just said that the derivative of the sum is the sum of the derivatives. Okay? In the next lesson, in 3.4, we will look at products and quotients of derivatives, and they do not follow the mold. So that's why I've been trying to highlight every time we've seen the mold, say, hey, this makes sense. But then when we get to products and quotients, realize it doesn't work out the way you might hope. It would be nice if derivatives of products and quotients would just follow, as you would expect. I don't even want to say what they would be. Okay? But there's two complicated rules there, your product rule and quotient rule. All right. So we can now put all of this together. Let me go ahead and just rework this problem. We did this last time. We can now put all of this together. Put all those rules together into one problem. Okay? So if I want to find the derivative of this function, well, first of all, this function is comprised of several terms. The sum rule right above us says, hey, if I want to take the derivative of several terms, I can just take the derivative of each term separately. Okay? Then within each term, I've either got a power rule or the constant rule or some combination of the constant multiple rule and the power rule. Okay? So we talked about this first one already. This would give me minus 24x to the 7th plus 14x to the 6th plus 4, and I'm going to go ahead and write it this first time. I'll write plus 0. Doesn't matter. You write minus 0. It doesn't matter. Okay? Normally we just don't write that, but I want to emphasize what happened for this last term? This last term is called a constant term, and the derivative of a constant is 0. Okay? Let's look at this right here. I could think of this as 4x to the first power. And if I take the derivative of 4x to the first power, I would bring down the exponent. Okay, that's 4 times 1, x to the subtract 1 from the exponent, right? But what is anything to the 0th power? Okay. So the power rule does help me take the derivative of that term. Okay. So you're welcome to think of it through the lens of the power rule. Okay. I would argue that a more sophisticated way of taking the derivative of 4x is to say that 4x is a line, and a line has a constant rate of change. A line's constant rate of change is just its slope. So when I ask how is a line changing, it's changing by its slope. So how is the linear term 4x changing? It's changing by 4. That's a more sophisticated way of looking at it, but it still works with your power rule. Okay. How are we doing? Give me thumbs up, thumbs down, and let's give me I'm tired. Yeah, that's what I thought. Okay. Any questions on this? Okay. In 2 days, this will be the easiest thing in the world for you, I promise. Okay? You'll be happy when you see a problem like this to take its derivative. Okay? But right now, you're still getting used to it. So I need to know what your questions are.
More so on C.
What's that?
More so on C, looking ahead for problem C, not A. Problem
Yeah,
C.
we'll look at C here in just 1 second. Good, I like it. We'll look at that. Any questions about how, for instance, how did I get 14 here?
2 times 7.
The 2 came along for the ride, right? The constant 2 just came along for the ride. Then I brought down the exponent of 7 and multiplied it to that 2. Okay? And then I subtracted 1 from the power of x. Now, this is going to be very important, folks. It needs to be perfectly clear to me when you're working with the function and when you're working with the function's derivative. Okay? So notice I named the function for you. I gave it a name, f of x. Okay? Then when I wrote f prime of x, I wrote out the derivative. Okay? You can't write out f prime of x and then partially take the derivative but not finish it. Okay? So it needs to be perfectly clear where we're talking about the function and where we're talking about the function's derivative. Okay, so that's why I've been harping on you all along for labeling things. Keeping track, we've got functions derivatives, and we've got lines that represent the tangent lines at points. We've got a lot of actors at play here. I can keep them straight. Maybe you can keep them straight. But we'll all understand what we're talking about if we label everything. Okay? All right. Let's. Somebody asked, how do we do C?
You could change it to s of t equals negative 4t to the negative third power.
So, yeah, so Freddie's exactly right. This is going to be a common skill in this class. Okay. We have somewhat limited rules right now for taking derivatives. So if you see a hard problem and you haven't learned a rule that will help you with that hard problem, my guess is you're going to have to rearrange the original problem first into a rule that you already know. Okay? Freddie says, hey, I've learned this power rule. I've got it. Let's see if I can apply the power rule. Well, the power rule doesn't apply here because I've got something divided by a power function. And we haven't learned how to do that yet. That's the derivative of quotient, actually. We haven't learned our quotient rule yet. But in lieu of doing the quotient rule, we could rewrite the problem, Freddie says. Now, have I taken the derivative? No, I have not. What did I do from the line that I was given to this line? I just rewrote the function. Right? Now, this is set up to use the power rule. Remember, I initially said in the power rule it's got to be a natural number, but then we gave what was called the generalized power rule that says, hey, it could actually be any real number, and this will work. Okay. So now we're ready to take its derivative, so I label it as s prime of t. This has to be completely clear. When are you working with the function? When are you working with its derivative? If you write chicken scratch and some of that chicken scratch is the right answer, I can't give you full points. Okay? All right, this gives us positive 12t to the what? Everyone write down what you think that exponent is. Positive 12t to the negative 4. Why? Because you subtract 1 from the exponent. Negative 3 minus 1 gives us negative 4. I can't tell you how often you'll put a 2 there. Okay, slow down. Okay. Now, I am not going to be a huge stickler for putting things in simplest form, but there are some things I'm going to require you to do. Okay? In my opinion, if somebody gives you a problem with no negative exponents, you should return that with no negative exponents. So let's go ahead and rewrite our answer for the derivative as s prime of t equals 12 over t to the 4th. Okay? That's just polite, right? Return things how you were given them. So says my mom. Okay? Okay. Boy, it's getting to be a cluttered board here. Letter B. I am going to do this problem the wrong way. Here we go. I'm going to say that y prime is equal to 2x times 3x squared minus 3. What did I do wrong? I mean, what's the derivative of x squared?
2x.
2x. What's the derivative of x cubed? 3x squared. What's the derivative of minus 3x? Minus 3. What's the derivative of 1? 0. What did I do wrong, folks?
Multiplications. You can't distribute the...
What is the big operation in this function here? We've got the product of two factors, right? Do I have a product rule? Well, you'll get one here in a little bit, but it's not going to be nice. The mistake that I made was assuming that the derivative of the product was the product of the derivatives, and I just took the derivative of each factor. That is a mistake. That is so wrong. Okay? That is the wrong way to do this problem. So what's the right way? Well, how could we do this problem? I'm asking you to.
Should we have to factor it out?
Distribute the x squared first.
Yeah, so let's get the vocabulary right. We're going to distribute the x squared. We're going to expand this out first. When you expand something, you write it as a sum of terms. And I do have a sum rule at this point, even though I don't have a product rule. So here's the correct way. Rewrite the original function. That gives me x to the 5th minus 3x cubed plus x squared. Okay. Now let's take its derivative. Okay. Let's go ahead and use Leibniz's notation just because I know you're still scared of it. Okay. That just says take the derivative of y with respect to x. It's the derivative, right? dy dx is equal to 5x to the 4th minus 9x cubed plus 2x. Did I make a mistake?
X squared.
Yes, thank you. Good catch. Everyone catch that? Okay. This is certainly not what I would have gotten if I tried to incorrectly use a product rule. Okay. So be careful with that. You'll step in it a couple of times. That's why you practice. You practice so you step in it well before the test and get it fixed. Okay? All right. All right, let's have everyone do letter C, or what is this, letter E real quick. I'd like everyone to do letter E. Quick.
0.
Is that the answer? I did the power rule. I brought down the exponent, subtracted 1 from it.
There's no x. It's all constant.
Yeah, right? So be careful. that power rule is kind of a powerful hammer, right? Not everything is a nail. Okay? So be careful with that. Nope. Okay? What is this function? It is a constant, right? It is a constant. What is the derivative of a constant? It is 0. You'll step in that a couple more times too. Okay? It's easy to do when you're in the middle of a long problem. Okay? All right. Let's do letter D. A prime of R would be what? R is the variable, right? Because how do you know that? Because I've written it this way. You know that the variables are. What is the derivative of this? 2 pi r. That's interesting, folks. What's the original function represent?
Area of a circle.
The area of a circle. What does its derivative represent? The circumference of the circle. That's a very careful. I've way oversimplified a very complicated topic. Okay, but if this is season 1 of the 3-season show, I've just dropped a little hint for what's going to be at the very end of this show. Okay, the culmination of calculus is Green's and Stokes' theorems, and there's a little bit of those two theorems those theorems illustrated here. There's something connecting the perimeter to the area related through derivatives. There's a connection there, but I am way oversimplifying it. Okay? All right. Folks, calculus is easy, some people say. It is algebra that's hard. Maybe that's a good point. We've learned this power rule. Okay? You could teach the power rule to a 3rd grader, right? Bring down the number up top, subtract 1 from it, right? Okay. How can I use my rules in this problem here?
Rewrite it.
Yeah, let's rewrite it. Okay. So you're going to need to practice this, and you'll see it in your homework. I could rewrite this as the square root of x over the square root of x minus x cubed over the square root of x. What did I do? I divided the denominator into both terms. Folks, please do not break my heart and do that. Please do not break my heart and do that. You can't cancel over addition like that. You have to first be able to factor out a square root if you're going to try to cancel it. So please. It's okay. You'll do it a few times. Okay, don't beat yourself up if you do, but get it fixed. Okay? All right. This gives us that y is equal to 1 minus, I'm going to write this as x cubed over x to the 1/2. I will normally from here on out do this next step in 1 step, but I'll do it in 2 for you here because we haven't done a lot with exponents. This gives us y equals 1 minus x cubed minus 1/2. Remember that? When you divide by exponents of like bases, you subtract their exponents. Okay? Normally I would have just jumped from this step to this step in a single step, and we'd have y equals 1 minus 6/2 minus 1/2, so that's x to the 5/2 power. Will?
The square root, it's how I see it is it's a thing that's to the power of 2, so you can just.
Well, so careful. So this can be written as x to the 1/2 power. Yeah. Was that your question?
Yes.
Good. Yeah. So remember with these radicals, like if I gave you the cube root of x, this one's a little more easy to see. The cube root of x can be written as x to the 1/3 power. And so you take, if it's a radical, you take 1 divided by the index of the radical. It's a little confusing on the square root because we never write the 2. I wish we would. Why don't we write the 2? What's that?
Start a petition, right?
Yeah. Let's get our congressman involved. All right. Y prime. Then now notice what I've done here, folks. This is where I need to know that you know what's going on. All along, I've labeled this expression as y because I haven't taken the derivative yet. Everything up to this point has been algebra. The calculus is usually in a calculus problem. The calculus is 1 step. In this step, I will take the derivative, okay? So that's going to be 0 minus 5/2 x to the 3 halves. Okay? I normally won't write that 0. This gives us y prime equals minus 5 halves. X to the 3 halves, great. I'm going to go ahead and do some rewriting with this. Y prime is equal to minus 5 halves times the square root of x cubed. That's one way you could write the problem.
You can just rewrite that 5 halves as 2.5 if you wanted to, or do you have to keep it in a fraction?
I leave things as fractions. I won't mark you wrong if you write 2.5, but we just, yeah, so somewhere in some class you were told, you know, don't write improper fractions. That rule is over. Okay? That makes no sense to me. And to all math people. We just don't do it anymore. So just leave them as improper fractions. Yeah?
Why, for the exponent of f,
Uh-huh.
For y prime, for the exponent of f, does it go down to 3x?
Yeah, great question. So what does our power rule say? It says bring down the exponent. Good with that? Then what do? We subtract 1 from the exponent. Well, what is 5 halves minus 1? Well, it's 5 halves minus 2 halves, which is 3 halves. Yep. Great question. Other questions? So I'm perfectly happy with this answer. That's great. Okay. I'm perfectly happy with this answer. You could say that that is the square root of x to the 3rd power. That's great. Okay. My math lab, I think, will sometimes want you to rewrite the problem this way, though, as minus 5 halves. Let me go back to this one here. Y prime equals minus 5 halves. And then say, well, I've got an x squared times an x in here, right? Hey, let me x squared times an x. So this gives me y prime equals minus 5 halves. Then this comes out, technically it comes out as an absolute value. Right? But notice that the original problem, this function has a domain of only positive values. So I don't need the absolute value on that. So we get y prime equals minus 5 halves x to the square root of x. And my math lab will often want you to write it this way. Okay? Like I said, I'm perfectly fine with this. So I don't require you to always simplify as much as my math lab will. But there are some things I ask you to do. Okay? If you're given a problem with radicals, then your answer should have, if it has fractional exponents, should have radicals in it. Okay? If you're given a problem with no negative exponents, then you shouldn't have a negative exponent as your answer. Okay? Now, do pay attention on your exam, practice exam. I often put do not simplify, meaning just take the derivative and walk away from it, because the simplification might be long and complicated, and it doesn't. I've already tested you on what I want to know that you know. Okay? I didn't give you enough room for that problem. All right. Folks, I hate to say it, but I'm not going to do a lot of examples like this one in class. We'll work this one here because it's got a nice picture to go with it. Okay? At this point, every time, and this is hard, every time I introduce a brand new topic, you have to immediately assimilate it with all of the other topics we've done. And that's tough. And I'm not saying it isn't. And that's what you'll work for in the homework. But I won't always do an example of all the possible ways you could assimilate the new topic with the old ones. Okay? We've learned how the derivative gives us the slope of a tangent line at a point, right? And what is the slope of a horizontal line? 0. Okay? So you can put your now new calculus skills together with all of your old algebra skills to answer this question. Okay? So let's work through it. Okay? So I've got this function y equals x to the 4th minus 10x squared plus 9. Okay? So I'm going to go ahead and write it this way just to kind of keep you on your toes. see how I'm rewriting y so it's more explicitly listed as a function of x? Okay. That's all I'm doing there. All right. So we want to know, where does this particular curve have horizontal tangent lines? Okay. So what are we going to do? Well, if I want to know where it has a horizontal tangent line, let's come up with the formula that will always give us the slope of the tangent line. What's that formula called? The derivative. So we get y prime of x is equal to, everyone take the derivative of that. Okay, check with your neighbor. Do you two agree? Okay, how do we do? Okay, anyone want to talk about it? Will? So we brought down the power, then subtracted 1 from the exponent, right? Okay. And then we've got negative 10. This constant negative 10 just comes along for the ride. I bring down the new power, so I'd have negative 10 times 2, which gives me the negative 20. Then subtract 1 from 2, which gives me an understood 1 there. I won't usually write the 1 there, but if you want to write the 1 there, makes it easier for you to see, you're welcome to. Okay. Of course, what is the derivative of a constant term? It's 0. Okay. Be careful with that. Constant terms have derivative of 0. Constants times a function, those constants come along for the ride. Okay. All right. So, this is a formula. You input any x value, it will output the slope of the tangent line there. Okay? Let's scroll down to our graph. I'll pretend it's not there. Let's suppose we inputted negative 1 into the derivative. What is y prime at negative 1? This has nothing to do with the problem. Okay? We'd have 4 times negative 1 cubed minus 20 times negative 1. What does that give me? That gives me a positive 16, I think, right? Because that would be minus 4 plus 20, positive 16. Okay. It's hard to tell this because of the scale, but what have I just said? Well, blue is my function, right? Blue is our y of x. Okay. Yeah. Oh, sorry. Well, but you might be able to trace. That's why I made it so big. So the one that looks like a rounded out w, okay, that's the function. Okay? So, what are we saying here? We're saying, hey, if we go to negative 1 and we draw a tangent line right there at x equals negative 1, what is the slope of that tangent line? Slope of that tangent line is 16. How can we see that another way? Well, the second function that I've put up here as red, I know you don't have it as red, the second function that I've put up here as red is the derivative. It is y prime, right? If I go to this point on the graph, what is this ordered pair right here? It is the ordered pair negative 1 comma what? 16. This is oh so important that you recognize this connection. Okay. The derivative takes the x-coordinate and outputs the slope of the tangent line at that point. Okay. Notice that the derivative in no way tells me what the y-coordinate is on the original function. Okay? So this was the ordered pair negative 1 comma 0. Great. Okay? The derivative doesn't tell me anything about its height, the function's height. It tells me about how the function is changing. This is very important, folks. If I were down in the Grand Canyon, the derivative couldn't tell me what my elevation was. It wouldn't know that I was, well, let's say I was down in Death Valley. Sorry, wrong formation. Let's say I was down in Death Valley. Okay? The derivative could not tell me if I was below sea level or not. But it can tell me if I'm currently walking uphill or walking downhill. Okay? I could be walking uphill below sea level, or I could be on a mountain walking uphill. The derivative would recognize that I'm walking uphill, but it wouldn't know what my elevation was. That's a common mistake that people make. Okay? All right. So, that was just kind of a quick example that I think was worth showing you about how the derivative works. Okay? Let's get back to the problem. Our question is where does this function, y, have horizontal tangent lines? So what am I going to do here? So, yeah, that's a good question. Do I want to take y prime of 0? Is that what I want to do? Let's stop and think about that for a second. It's a really good guess. But what does this give me? It gives me the slope of the tangent line when x is 0, right? Y prime of 0, oops, that's going to work out because the slope of the tangent line there is 0. But it wouldn't give me all the places. So what am I after? I'm after finding this place right here, this place right here, and this place right here. All the places where the original function has horizontal tangent lines. So I don't want to input 0, although it would give me an answer in this case, but it wouldn't give me all the answers. Okay? But generally, we don't input 0 because that would just say, what is the slope of the tangent line at 0? I want the slope of the tangent line to be 0. So what am I going to do?
Drop 4x.
What's that?
That drop 4x.
Well, you're on track.
Set y prime equal to 0.
Let's set the derivative equal to 0. We're going to set the derivative so that the output is 0. Okay? Folks, if you are still confusing input of a function versus output of a function, come by and see me. We'll talk about it. Okay? If you missed on the test, if you missed the first 2 questions, one of the first 2 questions, then there's something you're missing about input and output of functions. Okay? I am setting the output of the derivative to be 0. And then I'm going to find the corresponding points, x values, so that the output will be 0. Okay? So when we do this, we have, well, what was the derivative? We said it was, I think we said it was 4x cubed minus 20x squared. Is that right?
Just minus 20x.
Minus 20x, thank you. That's what we said was the derivative. Okay? What have I got now? An equation to solve. Okay? Let's solve that equation. I can factor out a 4x, and that leaves me with x squared minus 4.
Minus 5.
Minus 5. Sorry, folks. I think that's about 32 today.
28.
Okay? Now, and I think this is what somebody was saying, factor out the 4x, yeah. But we had to, the key was to set it equal to 0 first. Okay? So then by my 0 product property, we have either 4x equals 0 or x squared minus 5 equals 0. This tells me that x equals 0 is one place where the output of the derivative, this is very important, where the output of the derivative will be 0. Not the output of the function, the output of the derivative. Or x squared is equal to 5, or x is equal to plus or minus the square root of 5. What am I saying? I'm saying that the 3 places where this function is going to have horizontal tangent lines is at x equals, hang on, just get my butt kicked. Is at x equals minus the square root of 5, at x equals 0, and at x equals the square root of 5. This is very important, folks, where the derivative is 0. I know you don't have color on your graphs. Where my red graph is 0 is precisely where the blue graph has horizontal tangent lines. Wherever the red graph is 0, that is where the blue graph has horizontal tangent lines. Okay. Notice some more. I mean, we've said this a few times. Wherever the red graph has positive y values, the blue graph is doing what? Increasing. Sometimes it's increasing with negative elevation. Sometimes it's increasing with positive elevation. The derivative doesn't tell me about that. It just tells me that it's increasing. Michael?
Is the blue graph the derivative and the red graph is the function? Or am I just...
Nope. So the one that looks like a W, and that's why I made it so big on your paper. The one that looks like a W is the original function. It was a fourth degree polynomial. Fourth degree polynomials can have up to 4 zeros, and this does have 1, 2, 3, 4 zeros. Whereas the derivative was some sort of cubic. Okay? The derivative was some sort of cubic, and the cubic can have up to 3 zeros. Okay? So this is that cubic shape. Yeah. Questions on this? Sean?
If we have something akin to this on the test, how do you want us to write the end?
Sure, great question. So at x equals 0, x equals the square root of 5, x equals minus the square root of 5, y has horizontal tangent lines. Something to that effect. Yeah. To be honest, if you wrote x equals 0 and you've done it systematically, labeling everything as you go through, you get to here, I'll probably just accept that. But this is a nice way to summarize what you just found.
Would you give us the graph?
No.
I don't think so.
No.
I don't think so.
No, because what could you do from the graph? You could identify the answers from the graph. Right? Now, that's not to say I might give you a graph and ask you to give me some information about it. I'm not going to say I'm not going to do that. In fact, I'll do plenty of problems like that. Okay? But for this problem, you're showing me how you analytically, and this is important, right? You analytically found, using algebra, and calculus, you found where we had horizontal tangent lines. If you remember, in college algebra, you learned how to graph polynomials. You learned how to graph lots of functions. But generally, what were you told? The teacher said, don't worry about where it turns around. Don't worry about this turning point right here. Just, you know that, because in algebra, you learned how to find this 0 and this 0, and you learned, the basic shape, and then you just put somewhere down here, you had a turning point. And the teacher said, don't worry about where you put the turning point. Well, we now have the tools to be more precise. Calculus is what's required to find where this has a turning point. Great. All right. So, again, I'm doing these examples now. These examples will continue to happen throughout the rest of taking derivatives. Okay? I'm not always going to do one in class. Here's a function. We're told that it represents position, and I'm asking you to find the acceleration after 2 seconds. Okay? So you have all the tools you need to do this problem. We're given a position function, right? So how do I find the acceleration of a position function? I'm going to take the derivative once, and it'll give me the velocity. And then Stephen says take it twice, and you get the acceleration, right? So let's write it like this. The velocity, which is equal to the first derivative of the position function, would be 4t minus 10. True? Then the acceleration, which is the derivative of the velocity, which is the second derivative of the original function, is equal to 4. Folks, you don't have to write out all the things it could possibly be. I'm just showing you how they're all interrelated. Okay, so you could, if you wrote v of t and then a of t, I think that's probably best. But if you wrote s prime and then s double prime, that's fine. If you wrote v of t and then v prime, whatever. I know that these are all acceleration. So you don't have to list them all that way.
We're going to have a problem that asks for crackle.
I won't ask you for a snap, crackle, or a pop. No. Okay. And notice, if you took the third derivative of this, you'd get down to a what? 0. And then you take the fourth derivative, you got a 0. Those higher order derivatives, as far as motion goes, aren't usually used because a lot of times, this is the path of a particle. What's it doing? I'm not really told. It's maybe moving back and forth on a line, or maybe it's an object flying through the air, something like that. Okay? Those types of motions are often modeled with polynomials. Usually second or third or first, second, or third degree polynomials is how we model them, and those quickly go to 0 when you take higher order derivatives. Yeah, I could ask you for that. It wouldn't be unfair, but I'm not expecting you to have memorized that the fifth derivative is a crackle. Okay. So yeah, I'm not going to ask, but that was just kind of just for fun last time. Yeah. All right. So I do want to see this work right here. I'm asking you to give me the acceleration when t is equal to 2, right? So we just said that the acceleration function is this constant function. But I still want to show you, what is a of 2? Well, everywhere you see an x, you plug in a 2, and what do you get out? 4. The acceleration after 2 seconds, acceleration at t equals 2, is 4 meters per second squared. What's that?
Is that right? Physics.
Yeah. Folks, how many of you had a physics class before? Out of curiosity. Handful of you? Yeah. How many of you done it with calculus?
Next semester.
Next semester. Yeah. Yeah. Hopefully not mathematical calculus. But if you've had physics before where you just had a bunch of equations, they'd say, here's this equation and here's this equation. That all makes a lot more sense once you've had calculus, because you see how all of the different equations are tied together through derivatives. Anyway. All right, moving on. So we're now going to learn how to find the derivative of the exponential function, e to the x. Okay? This is kind of an interesting argument that we make. And because this is your first pass through calculus, we're doing it backwards. Okay? Once you do it again, you can do it a different way. But so we're going to have to define, we've never defined e to the x in this class, and so we're going to define it now. Okay? So if I look at, here you've got the graphs, I'll just put it here. If I look at the graph of 2 to the x, okay, I could try to find the slope of the tangent line at x equals 0. Okay? And if I did so, I would find that the slope of the tangent line at x equals 0, so here I am, right? This is 2 to the h minus 2 to the 0. That's y2 minus y1 all over x2 minus x1. Okay? So I'm bringing in the secant lines closer and closer to get the slope of the tangent line for 2 to the x at 0. And what do I see? I see that it's pretty close to decimal point 0.69. Okay. By the way, I'm missing
Negatives.
actually yeah. So sorry, I see it's pretty close to decimal point 0.69. There's a typo in this, folks. There should be a negative sign for that one, because I came at it from either direction.
On the next column as well.
Yep. Thank you. Okay. If I did the same thing, but instead looked at the function 3 to the x, its graph would look like this, right? It's an exponential graph. Here's 3 to the x. It's really hard to tell the difference between the two graphs until you actually put points on it. Okay? Recall that all exponential functions pass through what ordered pair? They all pass through the ordered pair. Uh-oh. I'm not getting a resounding 0, 1. Anything to the 0th power is 1. So what do all exponential curves pass through? The order pair 0, 1 prior to any transformations. All right. Let's draw this tangent line right here. Okay. As I bring my h value closer and closer to 0, I'm getting a better and better approximation of the slope of this tangent line. Okay. And as I come at it from the other way, I'm getting better approximation. This should have a minus sign there. Don't worry, I fired my table guy last semester, so shouldn't happen again. Okay. What do we see that the slope of the line appears to be approaching? We see that the slope of the tangent line appears to be approaching something like 1.09. Okay?
Would you round up on the third digit?
Sure, yeah, 1.10. Good. Yeah, that's fine. Good. So, this is the exponent 2 to the x. This is the exponential function 3 to the x. I could look at the graph of f of x equals 2.5 to the x power. Much more difficult to calculate values for that. Okay, but you could do so. And it would have a slope. What would the slope of 2.5 to the x power be? What was that, Mike? It would be between 0.69 and 1.10, right? So here's the key. Somewhere in between the number 2 and the number 3, there is a number that when I take the slope of the tangent line of that number at x equals 0, I'll get 1. That's what I'm after. I would like to find some exponential function. It'll be 2 to the something, 2 point something to the x, 2 point something to the x, so that when I take and find the slope of the tangent line there, I get 1. I could guess and test to try to find that. I could try 2.5 and I'd be too little. I could try 2.9 and I'd be too big. I could try 2.8 and I'd be too little. So it's somewhere between 2.8 and 2.9. And I could keep checking that, and eventually I would find that the slope that makes that happen is this number right here. Okay? That number right there, that's just a decimal approximation of it. Okay? That number right there, we'll call E. I'll let the cat out of the bag. We call it E because it's such a messy number to write out. Okay? That number right there has a slope of the tangent line at x equals 0 of 1. That's why we pick it. Okay?
Can you go back?
Yes. And so, in fact, I'm just returning to this picture here where I'm going to say the same thing. So this number is going to be E. Okay? So this formulation gives us a more sophisticated way of defining Euler's number, folks. Please don't call it Euler. Okay? The other night I was listening to the rapper Eminem. Okay, so don't call it Euler. Right? I won't pick on your folks. You don't pick on mine. Okay. We want E to be the number so that the slope of the tangent line to the curve right here at x equals 0 is 1. And it turns out through a process of guessing and testing, we would get a decimal approximation for E. Okay. There's more sophisticated ways to come up with E as well, but we're not going to do it in this class. Okay. Now, what does this mean? Well, this means that if we look at the slope of the tangent line there at x equals 0, we would take that as the limit as h approaches 0 of e to the h minus e to the 0 all over h minus 0, right? That's how we'd write that?
Sure.
I could do x here, but I want h for the next problem. So I could have x approaching 0, and this would be e to the x minus e to the 0 all over x minus 0. It is the definition of the tangent line at x equals 0. Okay. But help me out, folks. H minus 0 is just h. And e to the h, well, we'll leave that alone. Minus 1. Okay. So what did we say that the slope of the tangent line at x equals 0 has to be? 1. We defined e so that this limit would happen. Okay? All right. We need that. I spent 10 minutes on it because it's important for what we're about to do here. Let's give the definition, or let's use the limit definition of the derivative to find the derivative of e to the x. So f of x equals e to the x. F prime of x then is equal to the limit as h approaches 0 of e to the x plus h minus e to the x all over h. Everyone see what I did there? What's that?
Maybe not.
Maybe not? Okay, so remember, what is the limit definition of the derivative? It is f of x plus h minus f of x all over h, right? So this is equal to the limit as h approaches 0. What is our function? It's e to the x. So I'm going to replace e to the x with x plus h. So that gives me e to the x plus h minus, I'm going to replace f of x with just e to the x all over h. Okay, that's where we are. Okay. Now, I'm going to use my exponential properties for multiplication and say that I could rewrite this as e to the x times e to the h minus e to the x over h. Everyone see what I did there? If I lost you, how would you combine these two? E to the x times e to the h is e to the x plus h.
That's the sum thing.
What's that?
Is that the sum?
Yeah, it is. It says that when you multiply two exponents together of like bases, you add their exponents. I'm using that property sort of backwards to say, hey, I've got addition inside the exponents, so I can break that up as multiplication outside of them.
Sort of the opposite of what we saw earlier, where we had subtraction of the exponents.
Yes, yep, good. So this gives me the limit as h approaches 0 of, now, oops, hold on, need a little room there. We did this trick once before. What is my limit? What is my limit variable? H. H is the variable that's getting smaller and smaller. E to the x then is constant as far as h is concerned. It does not depend on h. So I can factor e to the x out of that. So that's a tricky move, folks. We haven't done that before. And that's what I'm left with.
Did we say that was
And you
equal to
can't
1 above?
cancel the e to the x's because the e to the x is being multiplied by e to the h.
Right. So these two, I mean, well, yeah, they don't add out because this is like if I have 2x minus x,
Yeah.
I can't cancel the x's, but I could either simplify it, in this case I can't, or factor out an x.
Can you show the step before take the constant out? Where you factor
This
out
step?
Yeah.
Oh, I see what you're saying. Yeah, sure. Let's do that. So I could write this as the limit as h approaches 0 of e to the x times e to the h minus 1 all over h. So all I did was factor the e to the x out of the numerator. And then let's pull it all the way out of the limit. So you don't have to show that step, but it kind of midway stops that factoring process. Okay, so how close were we paying attention the last time? What is this limit right here?
1.
It's 1. Because of the way we defined e, we said this limit would come out to be 1. There's the derivative of the original function. Wait a minute. This is kind of interesting. Anyone here from Kentucky? All right. We just took the derivative of e to the x, and what did we got? What did we get? E to the x. Right? This is the Kentucky function. E to the x is its own derivative. Right?
I thought that was a Tennessee.
Sorry, my brain's glitching. How did you go from e to the x limit, whatever,
Mhm.
and then it just ends up being e to the x times 1?
Okay, look up above. This limit is 1. No, that's okay. That's okay. I mean, it's a hard substitution. That's why I spent, but we had to do this work first. That's why we spent the time talking about the slope of the tangent line there, because there's no other way to do this limit definition unless we can replace that with the 1. So, the derivative of e to the x is e to the x. Okay? All right. So, let's find some derivatives. What is f prime of x here? It is 3e to the x. Okay, careful, there's a lot happening there for me to write the exact same thing. The derivative of the constant, when I take the derivative of a constant times a function, the constant just follows along, and then what is the derivative of e to the x? It is e to the x. Okay, so it looks like nothing happened, but there was stuff happening. Okay, all right. dy dx is equal to, what's the derivative of e to the x? E to the x. What is the derivative of x to the e? So what does the power rule say? It says if you have a base that's a variable raised to a real number, a fixed real number, bring down the base. I'm sorry, folks. Bring down the exponent times x, and then what do you do to the exponent? Subtract 1 from it. Okay. This is really important that you start recognizing where is x in your problem. If you've got an exponential function, an exponential expression, where is x? Is it the power or is it the base? Because that matters. Okay? You're not used to paying attention to that. Is x in the power or is it in the base of the exponential expression? Okay? When it is in the base, you use the power rule. Okay? If it's e to the x, then we use the fact that the derivative of e to the x is just e to the x. Plus, what is the derivative of e to the pi? What is e to the pi? So what is it? So what's our variable here?
It's just a fixed number, so it wouldn't be 0.
Yeah, what's our variable? X. Where does x show up in this expression? Doesn't. So what's the derivative of e to the pi?
0.
It's 0. Okay. Just for fun, we'll do it one time in this class. There's Newton's notation for the derivative. Okay. S prime of t then is equal to 1.8 e to the t plus 0. Because what is pi to the e? It is again just a constant. What's that?
I was asking about the notation.
Yeah. So I mentioned this a couple days ago. If this is a function that's dependent on time, and I take its derivative, I can also denote the derivative by just putting a dot over it. This is the last time I'll do it in this class, but you'll see that in other courses where you take derivatives. Okay. Let's look at this one. Let's say that y of x is equal to a e to the x plus e x to the minus 1 minus e x to the minus 2. Folks, did I just take the derivative?
No.
How do you know?
You didn't set it to prime.
Because I labeled the function, and it's still the original function, right? You see why you have to do that? So other people can follow your work? Okay. I know there's a few of you out there that still didn't write it. Okay. All right, now let's take the derivative. Y prime of x is equal to a e to the x. Why did this a just come along for the ride? Because it's understood to be a constant, because what's our variable? X. Okay. Minus e x to the minus 2 plus 2e x to the minus 3. Can you see that, Will? Over here. Okay. I was going to try to drag it over so you can see it better, but I can't. I'll try. Okay. So notice what happened here. I brought down the exponent. That's where that minus sign came from. Subtracted 1 from a negative 2. Sorry, subtracted 1 from a negative 1, which gave me negative 2. I brought down the negative 2. That's where the plus sign came from. 2ex, subtract 1 from negative 2, you get negative 3. Folks, be polite. How was this problem originally given to us? With positive exponents. So we return it this way.